Gaussian elimination is the algorithm that we're going to use to try to put everything into a diagonal reduced echelon form. Unfortunately, not every system is going to give us this. Now, as an example, I've written a system here, and this is in echelon form, but it's not in reduced echelon form. In this bottom row is essentially a 0 equals 3. Now, the variables in our system here are x, y, and z. When you solve a system, you are trying to figure out which values of x, y, and z will make the left and the right equal for all the equations. Now, when you encounter a 0 equals 3 like this is what we call a contradiction, something that's always false. No x, y, z will make the left-hand side equal the right-hand side. And if that's the case, there are no solutions. When you encounter a row like this with a contradiction, you cannot have solutions to your system. Another strange type of thing that could come up is with a system that looks like this. Here's the system on the left. You should row reduce to be able to get to something like this. We are in reduced row echelon form. In this bottom row, we see an identity, 0 equals 0. That's always true. So we don't really have to worry about that equation. It doesn't really tell us any useful information. Now, the variables in our problem, x1, x2, x3, and x4. We have pivots only in 2 of those columns. We have an x1 pivot and an x3 pivot. There are no pivots for x2 and x4. If we have a pivot in one of the columns, we are going to call that a basic variable. Basic variables correspond to pivot columns. And in our case here, x1 and x3 are pivot columns, so they are basic variables. There's something called a free variable, and these are columns with no pivots. So these correspond to non-pivot columns. In our particular example, x2 and x4 are free variables. Well, why do they call them these things? And the reason is how you should interpret the solutions. So from row 1, I'm seeing that x1 minus 7x2 plus 6x4 is equal to 5. And from row 2, I have x3 minus 2x4 is negative 3. If you have a basic variable, it's only going to appear once. Remember, a reduced row echelon form has zeros above and below. So that's the only time you will ever see that variable. That's why it's called basic. So I'll have x1 is equal to 7x2 plus 6x4 plus 5. x3 is 2x4 minus 3. The other variables appear more than once. The left-hand side can equal the right-hand side for any values of x2 and x4. That's why they're called free. You're free to choose them however you'd like. If x2 is 0, and if x4 is 0, the system will still have a solution. x1 will be 5, x3 will be negative 3, and the solution to our system is going to be 5, 0, negative 3, and 0. Now, if x2 is equal to 1 and x4 is equal to 0, x1 is going to be 12. I can just take this top equation and plug in x2 as 1. And the bottom equation is still going to give me negative 3. So the solution to the system, the numbers are going to be different. And you can see that I can do this infinitely many times. I can pick any values I want for x2 and x4. So I'm going to end up having infinitely many solutions to this system. The general solution is a 4-tuple of numbers. The solution has x1. Well, x1 is 7x2, 6x4, 5. x2, x3 is 2x4 minus 3, and then x4 is free. So once you understand row echelon form, and once you understand basic and free variables, you can summarize everything that's going to happen. Your only options are no solutions, exactly one solution, or infinitely many solutions. As soon as you have a free variable, you have infinitely many answers. It's not possible for you to just have 2 answers. If you've got some generic system and it looks like this, you've got a problem, because in this bottom row, you have a contradiction. In your coefficient matrix, you are missing a pivot. So a solution to the system exists if every row of the coefficient matrix has a pivot. And it's important to distinguish between coefficient matrix and augmented matrix. So if there's something in the right-hand side but zeros in the left-hand side, you're going to have a contradiction. This is what's called the existence condition. If every row of your coefficient matrix has a pivot, you will have a solution. The other kinds of things that can happen have to do with columns. So for example, if I give you a system that kind of looks like this, I have a pivot here and here. These are going to be basic, but right here I have a free variable. The system has infinitely many solutions when it has a free variable. So it has infinitely many solutions when you have no pivots in any columns. So if you are missing pivots, or a better way of putting it is that the system will have a unique solution, so it won't have free variables, if every column has a pivot in the coefficient matrix. So if every column of the coefficient matrix has a pivot, you will have a unique solution if you have a solution. So you have to be a little bit careful. If I give you a 2x2 system, here, every column of the coefficient matrix has a pivot, so I'm going to have a unique solution. But if I give you a system like this, yeah, you may have a pivot in every column of the coefficient matrix, but right here you have a contradiction. So ultimately there cannot be a solution. And the ideal case is when you've got a pivot in every row of your coefficient and a pivot in every column. You will get a unique solution. So if I end up with a situation like this, then I am in business. There's a pivot in every row of my coefficient matrix. There's a pivot in every column of my coefficient matrix. I will have no free variables. I will have no contradictions. I will have a unique solution. That's all there is possible. 0, 1, or infinitely many. If you have more than one answer, you have to have infinitely many answers. There's no mechanism in a linear system for you to have exactly two solutions.